In this video, we're going to be going over some example problems for the fundamental theorem of calculus part 1. So we're going to start off by stating the theorem. We have if little f is continuous on the closed interval a to b, then big F of x, which we're going to define as the integral from a to x of f of t dt, is going to end up being differentiable on the open interval a to b. And additionally, we have that the derivative of big F of x is going to be equal to our original function, f of x. Note, big F is going to be called an antiderivative of little f. And little f, like is stated here, is the derivative of big F, right? So what this theorem is essentially saying is that if we take the derivative of an antiderivative of a function, we get the function back. And we're going to end up proving this theorem and going more in depth in class. But for the remainder of this video, we're just going to be going over some examples that are more kind of computational and procedural. For our first example, we are finding the derivative of g, given that g is the integral from -4 to x of, and then we have this function. And this function inside, this is our f of t. This -4 right here is our a. And we basically have everything set up to just right away apply the fundamental theorem of calculus part 1. So when we're computing g prime of x, this is the derivative with respect to x. So if we want to be super specific, we can put d dx of, and then g of x. So integral from -4 to x of e to the 2t cosine squared 1 minus 5t dt. And right away, we can apply fundamental theorem of calculus part 1 and get that this will be equal to e to the 2x cosine squared of 1 minus 5x. And that's all we have to do for this problem, right? We just have the internal function. All right, the next example, things are tweaked a little bit. So instead of having the integral from, say, 1 to x, we have the integral from 1 to x squared. So the difference here between the last problem and this problem, why we can't just, right away plug in x into the internal function, is that we have a function of x, not x, as the upper bound. And so to do this type of problem, we're going to actually go back to chain rule. So if you recall chain rule, we have that if I have big F of g of x, and I'm trying to take the derivative of this, this is going to be equal to the derivative of big F of g of x times the derivative of g of x. Now, I used big F because in these types of problems, our big F is going to be the integral from a to x of f of t dt. And so when we're looking at big F of g of x, this is going to be when we have the integral from a to, instead of x now, we have g of x, f of t dt. And this is exactly the setup that we have for this problem. So our g of x is this x squared, right, highlighted in yellow. Our f of t is this sine of t squared. And so we just have a chain rule right here. We're trying to take the derivative. So we can go ahead and set that up. So h prime of x is going to be equal to, we're taking the derivative with respect to x of this integral from 1 to x squared sine of t squared dt. We end up getting sine of x squared squared, so big F prime of g of x, times the derivative of g of x. Well, g of x is thus x squared, so the derivative is 2x. And we can kind of just rewrite this into 2x times sine x squared squared gives us x to the 4th. And this is going to be our derivative of h of x. All right, we have one more problem. So we're trying to calculate the derivative of s, given that s of t is equal to this integral from cosine of x to 0 of, and again, we have this internal function of t. So one thing, which is the same thing that happened in the previous problem, is that we don't have x as a bound, we have a function of x. So again, we're going to be using chain rule. But the other thing is that these bounds, if we want to apply fundamental theorem of calculus part 1, kind of using it like a formula, we need to swap the bounds so that we go from a constant to our x or our function of x. So we can start writing out s prime of t equals, and we have d dx of this integral cosine of x to 0 arctan e to the t dt. And so the first thing I'm going to do is I'm going to swap my bounds. And if you think back to the properties of integrals, if we flip our bounds, we just make the integral negative. So I can pull that negative all the way out in front. So I have negative d dx of the integral from 0 to cosine of x of arctangent of e to the t dt. And now we apply chain rule like in the previous problem. If you want to pause the video and try to do that before I write out what the answer is, I would suggest trying that. So we've got that this is equal to negative. We've got arctangent of e to the cosine of x times the derivative of cosine of x, which is going to give us a negative sine of x. So I'm going to combine these negatives to make a positive, and then I have sine of x. And this is going to be our derivative. All right, so in lecture, we're going to go over the problem that I have listed right here. I would suggest if you have some time, go ahead and attempt this problem so that when you come into lecture, if there's any confusions or mistakes, you're ready to ask questions, you have questions ready for me. And then if you get it right, then perfect, and you know that you did everything right.